Okay, so we're going to look at another similar method of integration. This one is by substitution. So the way integration by substitution works is it takes something that you are unable to do and it turns it into something that we can do by substituting in a different value. Now, normally in a A-level question, they will tell you the substitution to make if they want you to use substitution. So, for example, in this instance, they're telling us we want us to use u equals 2x plus 5. And there's 3 steps we have to go to. Well, there's 2 steps and then 1 extra step if it's a definite integral. So let's go through those. So our first one, we want to replace every instance of x. Okay. So if we're saying that u is equal to 2x plus 5, then certainly we can replace the 2x plus 5 in our question. But there's also an x that we might want to do something with. So we're going to rearrange this. If we take away the 5 and then divide by 2, we should just get x on its own. So we're going to place that in place of the x. So let's see what this looks like now, after we've done step 1. X is going to get swapped out for u minus 5 over 2, and root of 2x plus 5 is going to get replaced with root of u. We still have dx, so we can't actually integrate anything yet, because if we're talking about powers of u, it needs to be with respect to u, so we need to change this to a du, but that's what the second step is about. So that first step, get rid of the x's. Second step, we're going to replace dx. Now, how are we going to do this? Well, we're going to go back to what we said before, which is that u equals 2x plus 5, and we're going to differentiate that. We're going to do du by dx, which is just equal to 2. And then we're going to rearrange that by multiplying across by the dx, and then dividing across by the 2 after that. So we're going to say du is 2 dx. So dx is a half du. And that means we could replace the instance of dx that we've got here with a half du. So let's do that. We'll have integral now of u minus 5 over 2 times the square root of u times a half du. So we've done step 2 now. Now we still need to integrate this, so it's not definite, we don't need to replace the limits. This is almost at a point where we can do something with it, so we just need to sensibly rearrange it now. Something we can do is we can take out a factor of a quarter. We've got u minus 5 over 2, and we've got a half, and those two multiplied together would give us a quarter, so let's stick that at the front. And then we also want to swap out the u square root. We want to make that a power, so we'll make that a u to the half. And then we still got our du. So what can we do with that? Well, we still can't really integrate it. We could use by parts, I suppose, but there's no need to. We can just expand out this bracket. So u times u to the half will give us u to the 3 over 2. 5 times that will give you minus 5u to the half. And we finally have something that is fully integratable. It's just powers of u. So let's actually do that. If we integrate that, let's go green now. We're going to end up with a quarter, and then u to the 3 over 2, so that's going to go up to u to the 5 over 2 divided by the power, and then 5, so it's going to go up to u to the 3 over 2 over 3 over 2. And we should remember we've got a plus c on there as well. So is that done? Well, it depends. Sometimes the question will just say integrate this in any form, but quite often it will say it wants you to give your answers in terms of x, and quite often it might want to say simplify it. So, you know, there are things we can do to make this a little bit nicer. So the first thing we could do is deal with those fractions. If we divide by 5 over 2, that's the same as times in by 2 over 5. So we could say this is 2u to the 5 over 2 over 5, and this is 10u to the 3 over 2 over 3. We still, I suppose, got our plus c over there. In fact, let's add the plus c right at the end, because, you know, it's going to get mixed up with some of the substitutions we make. And then, is there anything you'd want to do with that to make it simpler? Not really. You could give it a common denominator or something. You could take out a factor of a 15th, maybe. But I think that's pleasant enough. We can multiply in the quarter or something, I suppose. And we can make this 2u to the 5 over 20, so that would be u to the 5 over 2 over 10. and this would be 10 over 12, so that would go to 5/6 of u to the 3 over 2 plus c. And then our final step could be to put our x's back into there. So we know that u is equal to 2x plus 5, so we could make this into a tenth of 2x plus 5 to the 5 over 2 minus 5/6 of 2x plus 5 to the 3 over 2 plus c. I think that is about as simple as we can get it while putting it back in terms of x. Now it's important to note that there isn't just one substitution that would work in a given question, okay? So this is exactly the same question, but we're going to make a different substitution. We're going to say that u squared is 2x plus 5. And let's just see if this makes stuff easier, if it makes stuff harder, but we're still going to do the same thing. So we're going to replace all instances of x. So if u squared is 2x plus 5, then u is equal to the square root of 2x plus 5. So we can sub in just u instead of that. And we might also want to rearrange this. So u squared minus 5 over 2 is equal to x. So we can sub that in for our x. U squared minus 5 over 2 and then dx. So that's step 1. Step 2, we want to replace dx. So we're going to differentiate this, but we're not going to do du by dx this time. We're actually going to change this to u squared minus 5 is over 2 is equal to x. So we've already got that actually. And we could then extend that out to being x equals a half u squared minus 5 over 2. And we're going to do dx du this time. We're going to differentiate this with respect to u. So that would make this times by 2, decrease the power, it's just going to be u, and 5 over 2 goes away. And then we can multiply across by the du, and we'll end up with this as the substitution to make, which I think is it's a different one to what we made before, but that's because we're using something different as terms of what u is. So subbing it all together, we'll have, and let's take the half outside already, we'll have u squared minus 5 times u times du, well, with respect to u. Can we do anything with this? Well, yeah, we could leave the half outside, and then we could multiply this all out. So this is u squared times u squared, that's u to the 4. This is 5u squared, and yeah, that's good enough to integrate, isn't it? So if we actually integrate that, let's switch over to green now we're integrating. It's going to be half of a fifth u to the 5 minus 5/3 u cubed. And we'll have a plus c on here somewhere. We could then multiply it out. We'll end up with a tenth u to the 5 minus 5/3 u, no, minus 5/6 u cubed plus c. And we should be able to substitute in our thing now. So if u was equal to 2x plus 5 all rooted, so in other words, u is equal to 2x plus 5 to the power of a half, then u to the power of 5 would be, just raise that to the power of 5, would be to the power of 5 over 2, and u cubed would be to the power of 3 over 2. So our final answer here, and this is exactly the same answer we got on the previous question because it's the same integral, just done in a different substitution, would be a tenth 2x plus 5 to the 5 over 2, 5/6 2x plus 5 to the 3 over 2 plus c. Cool. So one way we use substitution is to get rid of those sort of awkward algebra bits, but we can also use things like trig identities and use it to get rid of trig as well. Here's an example that uses that. So we've got here the integral of cos sine x 1 plus sine x cubed dx. This looks pretty awkward, and we're going to use a little bit of a shortcut with this. So I said replace all instances with x. I'm just going to put some quote marks on this. You kind of replace the easy ones and you see if dx will get rid of some of the difficult ones. I'll show you what I mean with that. So we've got u is 1 plus sine x, okay? And we could also rearrange that to u minus 1 equals sine x. Why might I want to do that? Well, I don't really know anything nice I can do with cos x. I can obviously use cos squared plus sine squared is 1, but that's going to introduce some square roots, and I tend not to want those in my integrals, unless it's going to make life way easier. So I'm just going to leave that for a second. I'm going to sub in u minus 1 for sine x, because that's the rearrangement we did. And then this bit over here is u. cubed. So we have replaced most instances of x. Now what we're going to do with that dx? Well, I think the easy thing to find would be du dx. So let's do that. Du dx is equal to 1 differentiates to nothing and sine x differentiates to cos x. So in other words, if we swap the dx and the cos x over here, we'll get 1 over cos x du is equal to dx. And this is clever because we can now substitute that in, step 2 let's call this, and we'll have cos x u minus 1 u cubed and then times 1 over cos x du. What's good about that? Well, we can cancel out the cos x's. And so we end up with just having to integrate u minus 1 times u cubed du. So even though we didn't get rid of all the x's at the start, because that cos x looked awkward, the version of dx that we used got rid of it. What can we do with this? We could expand this out, u to the 4 minus u cubed du, and then we'll just integrate that. So that'll be u to the 5, or a fifth u to the 5, minus a quarter u to the 4 plus c. And then we could go ahead and substitute back in what we know u is. So we could say this is equal to a fifth of 1 plus sine x to the power of 5 minus a quarter of 1 plus sine x to the power of 4 plus c. Cool. So let's actually do an example that replaces the limits then, because we've only done step 1 and 2 so far. Similar question here. We've got x and we've got x plus 1. Both of those seem fairly easy to rearrange. We could have u minus 1 is equal to x, certainly. So let's go straight into step 1. We haven't changed the limits yet. X will sub out for u minus 1. X plus 1 cubed will sub out for u cubed. And then we've also got a dx that we need to deal with. You could do this by differentiating du, or you do it by differentiating dx. Let's find du by dx. So we'll get that by differentiating u, and that will give us just 1. And we can then rearrange that to saying that du is 1 dx. So du is equal to dx. That's a really easy substitution to make. So for step 2, we'll still got our limits are not fixed yet. We've got u minus 1 times u cubed and then times du, because dx is the same as du. Cool. And then part 3, we want to change the limits. Okay, so you've got to remember at this stage these are x values, both of them, and we want to change them to u values. So we've got basically x equals 2 and we've got x equals 0. Now we know that u equals x plus 1, so we can use that. U is equal to 3 if x is equal to 2, and u is equal to 1 if x is equal to 0. And those are the limits that will sub in here. So we'll go to step 3 and we just change them to 3 and 1. By the way, make sure they go in the right place. So we're putting 3 at the top because it was the value that went with x equals 2, not because it's the larger value. You can sometimes end with these values swapping position in terms of which is bigger. So let's expand out our bracket. So that'll be u to the 4 minus u to the 3. It's pretty similar to what we had on the previous question, isn't it? And then we can integrate it. So we'll integrate that. That'll go to a fifth u to the 5 minus a quarter u to the 4. And we don't have a plus c because it's a definite integral now. And so we need to sub in our limits, which were 3 and 1. So we'll have a fifth of 3 to the 5 minus a quarter of 3 to the 4. Take away a fifth of 1 to the 5 minus a quarter of 1 to the 4. Let's jump ahead a little bit. So we'll get 28.35 minus 0.05, and so our final answer here would be 28.4. Another option you have there actually is not to change the limits of u, to substitute back in at this stage what x could be, and then use your x limits. That should get you to 28.4 as well. Okay, here's another definite integral to consider, this time using trig. As I said, basically it's going to be an algebra or a trig question when you're using substitution. We're using u equals 1 plus sine x, And we're not going to change the cos x just yet, same reason as before, hopefully it'll go away. So pi over 2 and 0, cos x, and then square root of u. Well, actually, let's just go straight to saying u to the power of a half, because we know we're going to use that. That's step 1. Step 2, okay, so we'll do du by dx, which is equal to just cos x. So given we're substituting in what dx is, we can rearrange this to dx is 1 over cos x du. And let's substitute that in. So we'll have pi over 2, 0, cos x times u to the half times 1 over cos x du. And the great thing about that, as before, is that the cos x's will cancel out, and we have a super easy substitution to make, which is going to be just u to the power of a half with respect to u. But before we do that, let's change our limits. So our limits were pi over 2 and 0, and those were our x values. And we want to find our u values. So u is equal to 1 plus sine x, and remember, we are always in radians when you're integrating involving trig. Sine 0 is 0, so this is just going to give us 1, and sine of pi over 2 is 1, I think, so that's going to be 1 plus 1, so that's going to be 2. So there's our substitutions that we can make. We can change the limits to 2 on the top and 1 on the base, again, not just because they're the biggest, but because they're the ones that go with those values. We can then integrate this. Integrating this will increase the power and divide by the new power, so we'll end up with 2/3 u to the 3 over 2, no plus c because we've got limits, and we just want to sub in 2 and 1 to this. So let's do that. We'll have 2/3 of 2 to the 3 over 2, take away 2/3 of 1 to the 3 over 2. And I think this is probably one that you'd want to keep in exact form, because 2 cubed is 8, square root is root 8, I guess. So what we've got here is 2/3 lots of 2 root 2 minus 1. You could put it as a decimal as well if you wanted. So the last little substitution trick we're going to show you is one where we show a proof. So in this case, we're trying to prove that the integral of 1 over square root of 1 minus x squared is arc sine x plus c. This is a result that's given in the formula book for what it's worth, but you could be asked to prove it. And substitution is how we do it, using x equals sine u. So let's go through our steps. First thing we want to do is we want to substitute in our x's. We're going to get rid of those and replace them with u's. So we're going to change this bottom bit to 1 minus sine squared u. Now, what is that? We've still got a dx, sorry. What is 1 minus sine squared of u? Well, we know that cos squared u plus sine squared u is equal to 1. And we can rearrange that to cos squared u is 1 minus sine squared u. So if we were to square root both sides of that, we would end up with a statement that was also true. In other words, the square root of cos squared, which is just cos u, is equal to 1 minus the square root of sine squared, 1 minus sine squared u all square rooted. So we're actually going to use this as a way of simplifying the base of this integral. We're going to change this to 1 over cos u dx. We still need to do part 2 though, which is to replace dx, and we're going to do that by differentiating x equals sine u. So if x equals sine u, we can differentiate that. Dx du is cos u, and we could then multiply across to get just dx on its own. So it's cos u du. So let's substitute that in. We'll end up with this is the integral of 1 over cos u times cos u du. Again, we've got some brilliant cancelling out there. Cos u and cos u will go. And we'll just end up with the integral of 1 with respect to u. Nice. So what would that do? Well, that would just integrate up to u plus c. And what was u? Well, x is equal to sine u. So the way to rearrange that would be to do sine minus 1 on both sides. And we end up with sine minus 1 of x is just equal to, well, sine minus 1 and sine cancel out is equal to u. And the other word for sine minus 1 is arc sine x is equal to u. So we can substitute that in, and we can say that that is the proof that we were trying to make. Excellent. So for these next 5 slides, I am not going to go into them in the same amount of depth that I did on the first few. This is a question. I'd like you to try it. I'd like you to pause the video now and unpause when you think you want to see the answer. So pause now. And there you go. This is very similar to some of the other trig ones we've looked at, in that the differential cancelled out some stuff that was going to make it quite awkward. Cool. So using logarithms this time, remember you can differentiate a log to 1 over x. Pause the video now. Seriously, do pause it. Have a go. And hey presto, I did experiment a little bit with trying to rearrange this to x equals before deciding it was going to be too awkward. Fortunately, the du dx kind of got rid of the x situation for me. Okay, next one. Proof this time. Now we've got to put it in the specific form of log m at the end of all this. So pause the video now. Actually do. And there you go, should end up with log 16. There was a couple of subtle bits here. I think particularly when you're taking u as a square root, it might be tempting to think, well, why don't you take the negative one? There is a principle in integration that if you just write the words square root, you mean the principal or major square root, you mean the positive one. There's also some little log rule shenanigans you have to do towards the end. I think you can see here I was probably doing this in a bit more steps than I needed to do it. And it was another situation where the dx cancelled out really nicely with something that was being awkward in the actual question. So yeah, good question, that one. 2 more to go. So it's a bit of a two-parter here, where it's showing you what your answer should be looking like before you do the actual integration. And yeah, let's see how it goes. Pause now. So with this one, I'm going to be a bit charitable and say when they show it in this form, they haven't got around to changing the limits. That's like somewhere in the middle of section 2. Obviously, if you've got x values of 1 and 0, they're going to become u values of 2 and 1. So we need to make sure that we actually do change those when we get to step 3. You should end up with 3 over 2 minus 2 log 2. Wasn't anything particularly awkward about that one, although I guess expanding the bracket and remembering you can split that up hasn't been used for a while. Last one to go. Okay, the 5th and final challenge here. Best of luck. Do pause the video though, now. And there you have it. There's some sneaky stuff here where they had the 1 minus u squared, and you're expected to notice that is a difference of 2 squares that you can cancel out with the one that's below it. I think this is really difficult to do if you don't spot that. Again, you've got the major square root situation here to find your values for u. But otherwise, yeah, it was quite a nice question. Okay, nice one. That's integration by substitution.